Hello and welcome to part 3 of lecture 16 for Math 2 RO3. So we're talking about eigenvalues, and I ended off part 2 with this particular theorem which describing some equivalent statements for something to be an eigenvalue. And the first thing I want to do is quickly run through the proof. So let's explain why this is true. Well, let's say that lambda is an eigenvalue. So by definition, that means that t times v, or t evaluated at v, is equal to lambda v for some non-zero vector v. But now notice that this is the same thing as saying t evaluated at v is the same thing as first plugging v into the identity operator and then multiplying by the scalar lambda. But now we can rearrange this equation so we get t minus lambda times the identity operator evaluated at v is equal to 0 for some non-zero vector v. So remember, this is now just a linear operator. We have a non-zero vector v that when I plug in, I get something inside of the when I plug the vector v into this operator, I get 0, but the vector v was not 0 to begin with. So that means that the null space of this linear operator isn't 0. And because we're dealing with a finite dimensional vector space, the following facts all follow from the fact that v is a finite dimensional vector space, namely that t minus lambda I is non-injective. It means that this guy is also not surjective. And it also means that this operator is not invertible. And this follows from some results that we ended chapter 3 with when we were looking at linear operators. Okay, so you might want to look at chapter 3 again. Since v is not dimensional, it should be finite dimensional. Finite dimensional. So that's why those 3 conditions hold. Okay, so they're either all these are all true or they're all false. Okay, and in this case, they're all not injective, not surjective, or not invertible. Okay, so that's some conditions for an eigenvalue. And we also want the notion of an eigenvector for an arbitrary linear operator. And so as you might expect, is once you have an eigenvalue, the eigenvector is the vector that corresponds to that eigenvalue. Right? So let's formally write that out. Suppose t is a linear operator and lambda is an eigenvalue. A vector v is an eigenvector of t corresponding to the eigenvector if v is not 0 and tv is equal to lambda times v. Okay, so I've written this in red here. It is like the definition. This is like the definition in 1B03 that you would have seen, but now it's expressed in terms of linear operators instead of matrices. Okay, and as a corollary here, we have that v is an eigenvalue corresponding to the eigenvalue lambda if and only if. Another way of saying this is that v belongs to the null space of this operator. Okay, and this particular fact right here is actually coming from this line right here, right? V plugged into this operator gives me 0 for non-zero vector v. Okay, so there we go. Okay, and now kind of probably one of the more important results about eigenvalues and eigenvectors is the following theorem. Okay, so let's take a breather here and just kind of quickly take a second to read carefully what it's saying. So let's say we have a linear operator and we know that lambda 1 to lambda m are distinct eigenvalues, and here are some corresponding eigenvectors, v1, v2 up to vm. Then here is the really nice result about these things, these vectors, is that v1 through vm are actually going to be linearly independent vectors. Okay, so that's a great thing to know. Okay, and let's prove it. And the proof is by contradiction. So suppose that these vectors here are actually linearly dependent. Okay, so they're linearly dependent. Now, if they're dependent, there's going to be a smallest index k such that vk is in the span of v1 through vk, and v1 up to vk minus 1 are linearly independent. right? So you take your first vector, it's linearly independent. Then you take your second vector, is it in the span? No, well then it's linearly independent, right? So you keep building up. Because it's linearly independent, at some point you will find a vk that belongs to the span. And so that just means, let's rewrite this all, that vk is equal to a1 times v1 up to ak minus 1 vk minus 1 with some ai not equal to 0. We don't know which ai it is, but vk is a linear combination of these vectors. Okay, so that's our first fact. We'll call it star. We'll need star in a second. At the same time, what do we know? We know that lambda k times vk is equal to t times t evaluated at vk, because vk is an eigenvector. Right? So we can replace vk with what we know from the previous line. So this is equal to a1 v1 up to ak minus 1 vk minus 1. And then what we can do is we use the properties of a linear operator to rewrite this as a1 times lambda 1 times v1 all the way up to ak minus 1 lambda k minus 1 vk minus 1. Okay, so we're just using properties of linear operators or linear maps to get this right here. Okay, so let's go back to this is expressing lambda k times vk. Here's an expression. Over here, we have an expression for vk. So what we're going to do is multiply this expression by lambda k on both sides. So we get another way of expressing lambda k vk. Right? So lambda k times the vector vk is also equal to a1 lambda k v1 up to ak minus 1 lambda k vk minus 1. Okay, so now we have double star and triple star are two ways of expressing the same vector. And what we're going to do is subtract the second expression from the first expression. Okay, and so since they're both equal to lambda k times the vector vk, it should be equal to 0. Right, so here I'll write that out. So we have lambda k vk minus lambda k minus vk, and this is equal to, if you do all the arithmetic, expand out and recollect, you get lambda, oh sorry, I did it in the reverse order. I did this. I'm subtracting doubles, oh no, sorry, I had it right the first way. I'm subtracting this from the first one, and after I do all the arithmetic and clean it all up, I end up with this expression for 0. Okay, hopefully you can see all the indices there. And notice that here we have 0 written as a linear combination of v1 to vk minus 1. Okay. But we also know that v1 through vk minus 1 are linearly independent. That's how we pick the index k. So that means that all of these coefficients have to be 0 because they're linearly independent, right? So in particular, ai times lambda I minus lambda k is equal to 0. Okay. On the other hand, we know that all the eigenvalues are distinct. So the i's eigenvalue is different from the k's eigenvalue, and so this forces ai to be equal to 0. Okay, but notice that when we made this expression, we're saying that ai has to be not equal to 0. Okay, so this contradicts the equation star that we started with. So that means that our vectors had to have been linearly independent to begin with. Okay, so this is a great result because when we're looking at linear operators and we get eigenvalues and then their corresponding eigenvectors, you're actually getting collections of linearly independent sets of vectors. So in the last part, which I'll start in a minute, is looking at some consequences and some examples.